report of Professor Jager, and this is there are many news which we can take in our behavior, in our research, in the mode of research. Thank you.
Thank you, Professor Valonis, for the introduction. I will give an overview about our study programs at first, that you know where I belong to, what is JDC in Germany and Karlsruhe doing. Then I will give focus on the different research projects at our university. I have two presentations here yesterday on multi-sensor navigation, precise navigation, using GNSS sensors and inertial navigation sensors and camera sensors all together, sensor fusion. And today I will give a presentation at the University of Latvia on gravity field determination, on geoid computation, but we have other research projects as well. So I will give a complete overview about what is JDC doing, and then also give a short cut on the presentation of yesterday, on the perspective of today. This is my intention. But first to our study program. I myself am the head of the International Master Program. Just want to follow me. I think I have to get out here and start a new because that's a project. So, we have a faculty which is called Information Management and Media, with about 7 to 8 study programs. The 8 study programs, new master. On the left side of these study programs, you find the geodetic and geo-related study programs like JDC and Navigation, Geomatics Master Program, Geoinformation Management, then also traffic system management, also navigation related. And you find my lectures and my research in these two fields. They are embedded in the master program as well as in the bachelor program and directed to JDC. This is Karlsruhe Castle, our university campus, location in Europe. We have also a very big library together with a Karlsruhe University, classical university, the KIT, and so we have a good infrastructure for the students to study. This is our program of masters and bachelor. So the geo part is on the left side, JDC Navigation, and Geomatics, which is a master also for Geoinformation Management. This is a bachelor program with different specializations already in the bachelor, and you find myself on this left side of the different study programs. We have international relations to many universities in the United States as well as in Russia, and also in Latvia. And we have a double degree program with Spain, with a University of Polytechnics in Valencia. So the master program is a 4-semester master, which we have. So you will get 100 credit points based on a bachelor in some affine disciplines. So our challenge is to make a specialization in the master program directed to geodesy, as well as specialization directed to GIS, and as well as directed to programming. So we also do developments, not only theory but also practical realization of our theoretical concepts. This is about our double degree with Valencia. That means if you do our master program and you want to learn Spanish and spend 1 year in Spain, you can spend 1 year in our university and then go to Spain. Spain can come to us, vice versa. So it's very interesting for young students to study in two parts of Europe. So the modules in the first semester, all different disciplines are brought together. So we also accept civil engineers, for example, and then they get a focus on geodetic and GIS and geoinformatic fields in the first semester, and in the second semester already the specializations start. These are obligatory modules, and these are different modules related to satellite geodesy, digital image processing, signal processing, numerical methods, and directed to GIS specialization. You can already do specializations in the second semester, as well as in the third semester. Satellite image analysis, thematic visualization, geostatistics, physical geodesy, adjustment, mathematical geodesy, and engineering and photogrammetry and engineering geodesy are the elective modules, and these are the basic modules which you have to take. You see again, navigation technologies and mobile GIS is a theoretical part as well as a practical part. The students learn to program applications in navigation, and the fourth semester is the master thesis. So, now I will give some introduction by 3 to 4 slides on our research program, which are research projects. The first one is MOLPOS, European Union project, which is dealing with geodetic infrastructures for positioning services, and which is already finished, but we continue our activities in geodetic infrastructure for GNSS positioning services, because positioning services are coming up more and more and are also globally used. The classical geodetic positioning service works by terrestrial reference stations, which produce correction data, and which send the correction data via world standard RTCM to local positioning rovers, and then you get the position in the frame, which is defined by the coordinates of these reference stations. This is presently the standard. The development is going in another direction as well, parallel to this, namely to positioning by so-called state-space products. That means you do not send observation corrections anymore, you send by the internet to the users precise orbit, precise ionosphere model, precise troposphere model in a high update rate, so that you can directly make absolute positioning. This of course requires that you model a little bit more complicated. We have to consider then relativistic effects on the rover side, Sagnac effect on the satellite side. You have to consider the satellite clock and the rover clock synchronization. So that means you have to consider the Earth tides modeling. But this trend is to be seen. But it doesn't matter if you go to the relative positioning or you go to the absolute positioning. Absolute positioning is now in the range of 1 to 3 decimeters. Relative positioning already in a centimeter level, but they are in a competition, so to say. But what you need always are geodetic infrastructures. That means if you have got the position on the world, there are some different coordinate frames for the user, which you have to make accessible based on this position. The first thing is the geoid. You do not want to have the height over the ellipsoid, you want to have the height over sea level, and therefore you need a geoid computation. This is the topic of today. You also need to transform the position in different ways. The first thing is that you have to transform it from the present position on the Earth back to your frozen plate. So, for example, in Europe, our common frame is European Terrestrial Reference Frame 89. This is a frozen plate of Europe from the year 89. And from 89 to now, we have in Karlsruhe, depending on the location, about 80 centimeters of plate rotation. So if you want to have a precise position and you get ITF position, then you have to first rotate back to the old plate stand, and then you have to transform your position, if needed, in the national network, which can be different from the ITF network. The classical networks are still active and still needed, and this is the geodetic infrastructure part 1, to go to the still active classical networks with or without a plate rotation in advance. The second one, I already told it, is a transformation from the Lichtscheibe height to the physical height. And the third one is to provide these datum transformations in the horizontal position and the vertical position by a communication infrastructure, which is RTCM. And at present there is a worldwide standard which is called NGIP client, which can set up transformation messages and send them to the rover, so that the rover can direct have this position. We have also developed RTCM messages. I was involved in the international group to set up the new RTCM standard and the transformation messages. This was my task as a scientific leader of this industry consortium some 5 years ago, but now it's standard. You can have these RTCM transformation messages through the internet based on the messages which are generated by the service. The last topic is, of course, also necessary if you replace your million trigonometric points in a country by few stations. You have to monitor the stations to be sure that there is no sudden movement due to some sabotage or some geodynamic movement. So the services, they are monitoring round the clock their station position, and here we also do developments Monica is a reference station monitoring software which can also be used for the detection of geodynamic events and to de-risk vegetation. This is the first topic, geodetic infrastructures for GNSS services. Here you see what we have developed for Moldavia. We are computing transformation parameter databases. We are computing geoid models, and then this can be set up in a transformation message and sent to the user, for example, to transform the position in the Moldavian reference system to the Soviet old system SC42, or to transform the height from GNSS to the normal height. Normal heights are also relevant here in Latvia and European standard. We have done such developments for different, we have for Moldavia as well as for Brazil. We have also computed for whole Brazil transformation database, a transformation database for the whole country. You see here measures. That means we are computing local transformation parameters which are made continuous along the mesh borders, so that you have all a continuous transformation. This is one of our developments which we have done. And another topic where I will speak today at University of Latvia is the computation of height reference services. We started with a non-physical approach where we just set up the height reference service, the geoid, as a continuous polynomial service. Typically in the small measures, 10 by 10 kilometer measures, with a third order polynomial, and this is this part, finite element polynomial surface made continuous by continuity equations along the border, and this parameterization is then computed from identical points, from points which have height over the ellipsoid and height over sea level. The difference is just the surface. and we can also use vertical deflections here, deflections between the vertical to the ellipsoid and the physical plumb line as information, and we can also use classical existing shade models, which are then also mapped to this polynomial surface. Here we have done many computations worldwide. For example, here Florida. The software is also used at the Riga Technical University in the latest version, and was used in the frame of the PhD of Ms. Jan Paule to compute the precise geoid for Latvia. It is of course not possible to relate gravity measurements to a polynomial surface. Here you must have, of course, the gravity field as a modeling part. While vertical deflections can be derived from a physical point of view as well as from the geometrical point of view, so they fit here, but gravity does not fit. So we have changed our approach to a physical approach. And this is what I will talk today at the University of Latvia. You see it has 4 components. The first thing is that we have global geopotential models, and if you want to make a precise geoid, you have to have a resolution of degree and order 7,200 about, and that means we have 50 million of unknowns. So it is not possible to make a computation very comfortable. So what we are doing is to map the global spherical harmonics to spherical cap harmonics. Spherical cap harmonics are, so to say, the general case of global harmonics, where the pole is the north pole. In the spherical cap harmonics, you have a regional pole, and you can squeeze the whole Earth to a cap, and then you can save unknowns. That means you can model the local gravity field completely in a part of the world, and that is what we are doing. We span up a local cap, and then we map at first by an own algorithmic scheme the global spherical cap harmonic coefficients to the local ones, so that we have only some thousand unknowns instead of many millions. So, and in an integrated approach, we introduce these coefficients as basic gravity field modeling. They get corrections, recedals. We make a least squares adjustment, least squares estimation. And then that means the global gravity field defines the first part of the local gravity field, but of course with some recedals, and if you want also with some extensions to higher order. The gravity field, the gravity observations can then be related to this spherical cap harmonic coefficients here in this way, that we compute the parameters CNM and SNM here from gravity values. This is the observation, this is a parametric space, and this is a generalized Legendre polynomial, which with non-integer n, k is integer. So this is coming from this spherical cap harmonics theory. We can now also relate our vertical deflections, which are measured by zenith cameras, to the physical representation of the gravity field in spherical harmonics. You see the change of the geoid height in the direction to north is a vertical deflection to north, c, and the change of the geoid in the direction to east, index to the east, is a eastern vertical deflection component. So if we want to derive this, we can apply the chain rule, dn by dB minus dB by dn. This part is known. This is related to the curvature of the ellipsoid in northern direction. This is the curvature of the ellipsoid in eastern direction, and then we have to make the differentiation of the geoid, and the geoid is following the theory of Molodensky, Russian colleague from the last century. to be derived. So you have to derive the so-called disturbance potential in the direction of B, and the disturbance potential in the direction of L. And the disturbance potential is a function of the gravity potential of the Earth minus the reference potential of the Earth. The reference potential of the Earth is a GRS-80 potential, and so you have here the difference between the true potential parameterized by these coefficients and the reference potential, which you have to derive in the latitude of the ellipsoid. So you have, of course, not a parameterization in the latitude of the ellipsoid, so you have again to apply in several parts the chain rule. So you have rather long expressions, but the theory is complete. At the moment, we have implemented this part, but we have not implemented in our software. We always do software developments, this vertical deflection part. So this is something where another PhD candidate has to mind, this part, as well as other questions. So the fitting points are already implemented. That means the fitting points are these points where the surface should go through. The difference between the ellipsoidal height of the point and the normal height of a fitting point defines the quasi-geoid, and following the theory of Molodensky, this is just the Molodensky way to compute quasi-geoid normal height related heights which are related to the quasi-geoid. So you have again the parameterization of the disturbance potential as a difference between the true potential and the reference potential, which is on the right side. So what we are doing is not geoid computation or gravity field computation, which is uncontrolled. If you perhaps know the theory of Stokes, if you compute the Stokes integral by gravity measurements, we have no control what happens. You just integrate and get at the local position by the integral all over the world, so to say, or model with the Stokes function, the gravity anomalies. But if the gravity anomalies are wrong, partly you will not really detect the errors. Here, all measurement components are introduced as observations. So you have in the least squares, you get residuals, and you get control over your observations. This is the advantage of our approach, in opposite to others, that we have redundancy and we control the whole thing, the gravity field as well as the resulting geoid. So still in the old approach, the new approach is also presented today. We have computed again Brazil, and we have computed Latvia. It was further improved, the Baltic geoid, and the Latvian geoid has been part of the PhD of Ms. Jan Paule and was further improved in this frame. So this is about gravity field and geoid computation. What we are also doing worldwide is geomonitoring. That means we have developed a system which uses GPS receivers and total stations. This is a monitoring of a bridge in the harbor of Hamburg. And you see again, we use the data to produce three-dimensional positions of the moving points, and we then control the movement of the points by Kalman filtering processes and by displacement estimation. And here we have projects worldwide. This is one project in South Africa. This is one project in the east of Germany. We also have projects in Russia. We have a Russian cooperation partner. We have now a Polish cooperation partner, and we have now new cooperation partners in Vietnam. So we are also global players in geomonitoring. The thing is that we sell the software, and the local dealers, they sell their instruments and sell their service to install the whole thing. So it's a win-to-win relation on geomonitoring. This is another research topic, because the models for the monitoring are part of our research. What we are also doing is, instead of using classical sensors like total stations or GPS, to use navigation algorithms to set up local monitoring boxes where we integrate GNSS as well as inertial navigation sensors. And we do not make here a classical Kalman filtering. We are doing another estimation, Gauss-Markov model estimation, and algorithms where we can introduce restrictions. If you put such a navigation box onto a bridge or something like this, you can of course say the bridge will never incline too much, so you can give a limit to the movement of roll, pitch and yaw. And you can also say the movement of a bridge will not be 5 meters, otherwise you will not need monitoring anymore. And then you can also put some unequations on the position, and then these boxes get self-calibrating. Then in opposite to a normal inertial navigation system, which is drifting away very fast, there is a stabilization, and so we can make monitoring by using navigation algorithms. So this is NAVCA, another project. Monica is something for monitoring large-scale reference station networks. Our software is installed in our state as well as in Austria. Austria is also monitored by Monica. Monica is a software which computes permanently the state of a geodetic network in a large scale. Also corrects for plate rotations to find out internal deformations. This is also another research project at our university. And the last one is again physically and mathematically based. We are developing algorithms for precise out-indoor navigation for people, vehicles and goods, and georeferencing with distributed sensors and platforms. That means we always compute the full navigation state vector, which is more than positioning, consists of position, velocity, attitude, acceleration, rotation rates of a body, and some sensor calibration parameters. This is classical navigation state vector. What we are doing in opposite to classical navigation is that we always try to make a deep or at least a tight coupling with GNSS in favor of this navigation state vector, and we make a deep coupling of gyroscope data, accelerometers, magnetometers, camera data, barometers. So we have again redundancy on such boxes, and our topic is to make the algorithms. And here we have had 3 years joint research project with Baden-Württemberg industry, the big one, Siemens, Bosch, and smaller companies. They had some desires on navigation boxes they wanted to have, and we made the developments. I have already also brought some posters in small versions printed out, so you can see, for example, such a box. You can take one quick, and you also see the scope of our total research. You can also take one, and flight navigation is also a topic where you can take such flights. So this and I will present the results here. The second project is still running. This project is finished, so we have developed products and we continue to develop our algorithms. And the second one is to make a volocopter, not a drone, but a two-seater with 18 propellers. And so we have also another presentation in October of my PhD candidate who is doing this development, the flight control for such a volocopter. And what we are doing is to say we want to build navigation boxes with a lot of different sensors like this, and we want to place these navigation boxes somewhere on a body, so we have redundancy, we use several boxes, and of course a special case is also that the platform is the body itself, and another special case is that a platform is a smartphone. That means if you imagine you have a car where many sensors are in for automatic braking, for stabilization. These are also accelerometers, and you can imagine you put your smartphone into a slot and combine these sensors with your smartphone sensors, and the smartphone computes. And therefore you have different placements of your sensors, and you have lever arms. That means you have the position of the sensor needs some corrections in respect to the measurements of the and the body movement. So, if you are familiar with inertial navigation, you see that the first part of inertial navigation or of our navigation is to have a nice prediction model for the state vector from the old state to the new state. And here we have this prediction model in the permanent parameter estimation. The prediction of the new position, of the new velocity, of the new acceleration. We assume that for a short moment the rotation rate is constant of the body, and then we can update the old attitude to the new attitude by this Taylor series of an E function, which is a solution of a differential equation. So this is our state prediction. And now our observations are looking like this in a distributed constellation. You have a platform somewhere on the body, or in the special case, the body is the platform itself. And the platform is translated, the platform is rotated against the body. So you have to consider these so-called lever arms. You know where you screw the platform, so you know these parameters. On the platform which you develop, you have different sensors which have a translation in respect to the body, to the platform frame, and which have different orientations in respect to taking the observation. So if you think of a accelerometer sensor, the single acceleration of the chase accelerometer on the east platform is just a scalar product of the orientation of this accelerometer measurement unit with the acceleration in the platform frame. So this is what you measure if you relate all to the platform frame. The platform frame has to be rotated from the platform frame to the earth frame by using the attitude matrix. So you have here access first to the attitude, and by rotating then between the body and the platform, because the platform can be mounted ax parallel or non-ax parallel. So then we replace this part here, and we replace our the total acceleration at the platform being parameterized by the acceleration of the sensor in the E frame. That means this is the difference between the body, the sensor acceleration in the earth frame, minus the gravity field acceleration, minus the Coriolis acceleration, minus the centrifugal acceleration. But still at the sensor place. This is a sensor location. And now we must tell our algorithm that the sensor is somewhere on a platform, and the platform is somewhere on the body. And this is done in starting with this sensor-based equation by setting up the relation between the sensor position and the body position, considering the lever arms and this rotation between the body frame and the earth frame. So if we now replace the sensor location here, the first derivative of the sensor location here, the velocity, and the second derivative here, we have reparameterized the location of the sensor by the location and the velocity and the acceleration of the body. And this is what we are doing. We can then distribute our sensors on platforms and on the body and use a single observation and find the navigation state vector of our body. Because it's never possible to mount the platform directly in the center of the body. And in older times, the lever arms were kept very small. And we say we do not like this because we have now the age of MEMS sensors. Sensors can be distributed in very large lever arms. And so that it's also interesting then to use these lever arms as an information content. Because if you for example, have one sensor here and one sensor here, and you move the body, the accelerometers are also giving information to the rotation. So the sensors become self-calibrating and supporting each other. So we have redesigned the classical navigation algorithms in the last 3 years and now producing successfully products. So another product is this volocopter. You see it's a two-seater. It has 18 propellers. This is 180 meters. So it has 450 kilos. And this is a project which will be finished in next June 2015. The consortium are again 6 partners, one aerospace company from Baden-Württemberg, and our responsibility is to make the flight control for this volocopter, which is controlled by a joystick. And another thing is what we are doing is to use the navigation state to make surveying easier. So you can imagine if you have a small device to which you put a laser distance measurement, and you have the position from GNSS, and you have the orientation from the other sensors, then you can make a 3-dimensional polar computation of coordinates and can allow surveying for everybody. And we have developed this also for the industry, again for this company Texmo, which uses a ruggedized tablet PC with a GNSS on board, with a helix antenna, about 5 centimeters only, but for ordinary surveying objects it is enough, and laser distance measurement to catch the coordinates. What we are also doing is indoor navigation, again using inertial navigation, because indoor you cannot use GNSS. And what we are doing here is to navigate the foot of a body, because if you have only inertial navigation fused with barometers and magnetometers are critical in buildings, so you can forget them. Normally you cannot use them, so we can just put together accelerometers, gyroscopes with some redundancy inside, because they are very cheap, and we can also fuse barometers, but then we would have still a high drift. So we are saying, okay, we model the food, we make a small food sensor for professional securities, for police, for firemen, or for terror commandos, task forces, or something like this. This is our first development, and which is already working. And I can also show you some videos. The trick is that if we find out in parallel computing that the food is on the ground, we can say there is no rotation rate, there is no velocity, and there is no acceleration, and the position is fixed, and the attitude is also fixed. Then self-calibration becomes active, no? And then if it continues, the full navigation state vector is determined again, and so we can survive for about 10 minutes in a building without a big drift. So drift is then smaller than 1 meter after 10 minutes, and then we need again position information. The position information comes from the server at the moment in georeferenced buildings, or that means the user has his present position and the building in 3D on his smartphone, and then he gets the information. If you enter this, you find a control point, he gets a red point, and then confirms, and then the position is actualized. So this works, but we also think about other solutions. I will show you what we are doing. And so this is the server from this company where we are cooperating. We have developed the smartphone client, and they offer this service for police, for fire, and also for visitors walking through buildings. If you have a Chinese group visiting your factory and you don't want to have them spying, then it's better to see where they're walking. They get then a small shoe sensor and walk around, and this is the intention of this business. I already told you that we are using the same algorithms for structural health monitoring, for high frequent monitoring of buildings, and you can also have this presentation. All presentations are here. as well as this presentation. And you find a lot of links on this project NAVCAR, and I will show you, but now some videos of our developments. I will leave the PowerPoint presentation and go to some video. I hope I will work here. So the first thing is this Robinette box. This is this box, what you have also seen, with a GNSS antenna, helix antenna, which could also be smaller, and we have accelerometer, gyroscope, magnetometer, barometer, and so on coupled. And this is outside, so we can use GNSS, and you see the deep coupling leads to a very stable trajectory, even with cheap sensors. What is inside this box is a Mühlblock sensor for 50 euros only, and accelerometers for €1 and gyroscope, and you see what you can do. You must consider that this is absolute GNSS from the orbits. That means if you want to have the same trajectory on next day, you would have to make online precise point positioning or feed in the differential position. This is also possible, but for a short time the absolute position is also stable from the orbit, so it works very well. No drift, no? And yeah, permanent trajectory. And this is a commercial product which we are also selling. And we are selling, this is our firmware on the box, but we also enable the user to get down the raw data and make own modeling. So you can also have a so-called evaluation kit for own development. And our indoor navigation. For security, so this is, we have not had the shoe sensor at this time, so instead of a shoe sensor we use the smartphone. Smartphone is also a box, no? And that means this student which is running around here in this building, this is a level of detail 4 building, he is now walking through the building and without any drift or only a small drift with usual inertial navigation sensor and parallel threading of the foot state, and you see visualization. You see him visualized walking around here, and so. But this is not an optimal solution because he carries a smartphone at the shoe and not a shoe sensor, no? But it works. No? And so on. And this is our flight control development. We have different drones. We have a small drone. You see, this is just a very ruggedized drone. If it falls down, nothing is really happening. So this is our basic drone for daily use, for testing. And this is 1 year old or so, this video. Meanwhile, we have two 50-meter drones and this volocopter, which are flying completely with our hardware. We have also developed own hardware. That means we can also develop the complete hardware and yeah, for this drone. And yes. So this was my presentation on our different developments and research projects. If you have questions, I can also go to one of these presentations on navigation for more details from yesterday if you want. Or, yeah. So, thank you for your attention.
Any questions, please? Do you have patented many of these issues?
We had no time to patenting, so it was a situation where we had to deliver. My assistants got paid for 3 years for industrial products. So there were no patents because this was given to the companies, but the algorithms, this was written in the contract, the algorithms still belong to us. We are not allowed to go into competition for a certain time, but this time is only 1 year, and then they can continue of their own. We are doing other developments which could be patented because, for example, we are very sure that indoor navigation problem is solved by using optical sensor as well. I can perhaps show you from yesterday what we are also doing. The indoor navigation. So we have developed software also for smartphones which is working with real markers very well. But in buildings you want to have real markers because they don't look very nice. And then what we are doing is then to say if we have in future georeference buildings, you just have to use the building 3D model and rotate it to the earth frame, then you have absolute georeferencing. If then you use photogrammetric software and detect in the building some corners, then you can and have the building model, then you can say, okay, this corner is the corner of my building model, and I have coordinates. So you do not need any more physical markers. You can use virtual landmarks. So you have also absolute position in buildings. And what we are also using together with Fraunhofer Institute, this is one master thesis running at the Fraunhofer Institute for automatic navigation of this robotic car. You see a GNSS receiver here, and you see a stereo camera. And the stereo camera is taking permanent images and determines the change of the position and the velocity of this stereo camera, which is somewhere on the body, in respect to the environment. So, and this is called visual odometry. And there is open source software available at the KIT. And what we are doing is to take this open source software and to make a deep integration, a deep coupling to the rest of the data. And this works very well. So you have again the velocity from visual visual odometry, and you have this lever arm. The camera is sitting somewhere on the object and it's rotated in respect to the body frame. So this is an observation equation for your observation in relation to the velocity of the vehicle. And this is this lever arm, and this is the orientation attitude matrix, and this is a known orientation. So if you put 3 stereo cameras on, you can fully determine the 3-dimensional vector of the velocity, and you can also determine the rotation rate by exploiting the subsequent orientation of the images, of the objects from stereo images. And then you have 2 full observations related to the navigation state vector if you consider the lever arms. So KIT, they are not geodesists, they did not consider the lever arms, they also don't know deep integration, they are more informatic people, and also the Fraunhofer Institute, they have some physics, but they also forgot or did not apply deep integration. That's what we are doing. And so we are already developed for indoor, this is a room, a deep integration of a stereo camera together with inertial navigation. So you can see that you can, in a room, instead of GPS, use the velocity and use the rotation rate of this stereo camera. It is first derivative. That means we also have some drift. We have no absolute position, but the drift is much more slower, and you can use outside absolute positions from GNSS, and inside you can use this image processing on detecting by feature detection corners and other objects with coordinates. And if you make a deep integration of all observations, then the system comes to work very stable. So we will also write an article next 3-4 weeks, which will be titled somehow "Indoor Navigation is Solved," because we have all components, and now we are looking for industry to build such.
But you need before to have the reference frame. It means that you have to have a building.
Yes, you are completely right. But
you need to have in your computer, in your database.
Not. You can, okay, you are completely right, but I will show you two things. The first thing is that georeferencing of important buildings like main station, theaters, airports or something, where some accidents can happen or terrorism can happen, is a worldwide process. This is a world of level of detail 4 models. That means the Russians are doing this georeferencing of the important building, but also in our country, Berlin. The title is Smart Cities, Modern Cities, and Seamless Outdoor-Indoor Navigation. So public buildings are georeferenced. This is also a market. People make the georeferencing and sell the buildings, and the future will be that you are enter a building, you get from the service the building model as a database, and then you can navigate inside the building. So this is observed a new market level of detailed 4 buildings. And if you, for this visual odometry, if you do not have georeference of the building and you have sensor integration, you have to estimate the orientation of the building in respect to the Earth fixed frame. It means that you have additional unknowns. It becomes more unstable, but we, in our algorithms we have considered that the environment is not georeferenced yet, or it's georeferenced. It is a switch. But you are right. But we try to be always one step in advance to the others. So I have not a private company. I only have to pay my assistants. So and I have 4 people to pay, and we are directly cooperating with the industry. And I forgot many patents to make because of too much work. Patent is also complicated.
But for each project you have agreement with some industry.
Yes. We are selling our algorithms with protected codes as libraries. And we also sell it with USB dongles, small dongles, hardware protected. We never give the source codes to anybody. So because this is our top secret, and it works also in the gear monitoring. If we sell gear monitoring software to Russia without a hard key, you can forget it. They say "Spasiba Bolshoi," and then they are away. So you have to have a hard key protection, and we sell libraries. The same model is also for Xsense. Xsense is it's a Netherlands company which also does similar developments. I believe that we are already better than they have firmware which you can download, which is also protected on the chip. And we also develop firmware. If you go to the website NAVCA, you find firmware downloads, and we make special applications to use the raw data. And the applications are quite different. The modeling for a shoe sensor must be a multi-threading model, and so on. So we have also different application softwares. But patents for a university is difficult, because you must have money, you must go to the administration, I have a new patent, and okay.
Do you have also some other projects, for example, government? Is that your government?
Yes, the funding was by the government. The government funded 90% and the industry only 10%. So they wanted to have progress in satellite navigation.
But then you have to agree both. And private company and
yes.
government.
Yeah, this is a starting point. To have some papers where it's written that you are developing for the industry. You may not go into concurrency for 1 year after the end of the project. Or if you do something else, for example, this volocopter, we are not allowed to go into concurrency if they will use the software for 1 year later. But if we make scalable drones, at the moment we make scalable drones, this is not a concurrency product. And so we make small drones, medium drones, and Mr. Zwiener will tell about it, with a full closed loop of the regulation of the flight. If you throw away mass, if you make a fighting drone, you will change the momentum of inertia if you put out of the water, and then you have to readjust the physical properties of your object and so on. So it's very complicated, these scalable drones, and here's also a big market. So yeah, we are waiting for companies. If you have a companies who wants to develop drones, we have a full flight control, and if you deliver a naked drone, so to say, with a number of propellers, then we can make it fly automatically with joystick, with remote control. So yeah, and the same is for gear monitoring. We have better algorithms than the others. So we have no patent on the algorithms, but we sell it because our models are better. But we have to protect the software. This is, of course, very difficult if you make Android software, especially in apps and so on. So this costs also a lot of effort to make the software be protected. But
how many people are working in your team?
In the gear monitoring, there are working 2. One is doing gear monitoring, the other one is making algorithms, both for gear monitoring and for navigation. And in the navigation project, there are at the moment 3 people working. 1 on this airborne volocopter, and 2 on the basic algorithms for the other things. So I have, in principle, 4 assistants. I could have also 10, but I must get the money by myself. So I'm kind of research junkie, so, always looking for the next budget. So, but it works. So if you have good products, it's not a big problem, but you should not have too many assistants, because if you have also some social duties, so if they make a PhD, the money should at least be enough for the finishing of the PhD. So my optimum is 4 and up to 5 assistants. More are not possible. So because we have another, I don't know the infrastructure at university here, but in our type of university, the research must be done by external funding. We have only very few permanent research occupations. So I must make contracts with industry and so on. And that's why we have to produce whole products. I cannot say I make only theory. I like also theory, but from the theory I must go to the final realization. Otherwise I am not able to continue, because I cannot pay the assistants.
Do you have also some basic funding for research from government? Then you can
a few. I have a half place for assistant for PhD, but only 50% permanent, and I have another 50% research title. So I have one place which is fixed for forever, or for the next 10 years or so, due to the present structure. But this is only one of 4. The other 3 I have to pay from the products.
But as a professor of university, you receive your salary from university.
Yes. My salary, yes, of course, but not the salary for the assistants. So, but I can sleep quiet because I make yearly contracts, and if the project fails, my university is responsible to pay the assistant until the end of the year. So I have to pay back, but I have then a lot of time to pay it back. So this can happen. If I would have a private company, I would have to fire the man or the woman. So they have a safe position always for 1 year, sometimes 2 years, and PhD candidates for 3 years even. But 3 years are over, and then I have to look for the next funding. At the moment we have won the European satellite competition in Baden-Württemberg. We have first place out of 16. We have beaten other universities and industry. here, and so I will also get some money due to this prize, which I won last week with my team. So yeah, that's life.
Life is hard.
Yeah, it's one of the hardest.
Okay. More questions?
I have a question. What are the problems that you face in your work? Scientific problems.
The scientific challenges is in navigation, for example, that we have got that we went away from classical Kalman filtering. We do not do least squares. We say we approximate the Gauss curve by Laplace curve, and then we have another estimation principle, minimization, the absolute sum of procedures. And this is also typical for operations research algorithms. And if you go to this algorithmic world, you can then introduce unequations for the space, for the parametric space. And this is also a big advantage from our algorithm, that we can fix unequations for the unknowns or equations. If you do ordinary Kalman filtering, there is not a possibility, and we do sensor integration based on generalized maximum likelihood estimation. So we can also have other density functions. Perhaps you know the particle filtering. We can put different density functions together to one maximum likelihood, complete density function, and estimate from this. No? So we have also redesigned the algorithmic scheme, and otherwise we make sensor fusion. No? So we are not physicians, we are engineers. No? So we have not very big challenges. Of course, we also have to treat physics. No? If you go to absolute GNSS positioning, we have to model the Earth tides, we have to model all these relativistic effects. No? So what we are doing is, so to say, applied mathematics and applied physics. No? So I would characterize our work. No? Geodesy is our own science, minding this applied mathematics, applied physics to the body of the Earth and neighboring planets. And the challenge is complete redesign. We have beaten the classical design of the algorithms, because the situation has changed, the sensor world has changed. We have very cheap sensors, can distribute them, and there were no algorithms on the market for distributed sensors. So we had to redesign everything and start from zero. But it was a good idea, I think, because we have many requests from the industry for this algorithm.
Okay, thank you. More questions? No? Thank you. So.